Good afternoon. There's one of me, there's hundreds of you, so it's got to be louder there. I hope you had a productive day for those that were part of the conference so far. I now know that I stand between you and festivities later this evening, so I'm going to try and be short, and I'm going to try and be as direct as possible. So when I chose the title of this talk, I went back and looked at some of my previous talks to many of you in similar audiences, and I saw there was a lot of things like redefined, new frontiers, horizons, and they all had kind of over the last 5 years or so, had this overtone of accelerating the X scale. And I don't mean the old ARM architecture, was whether you talked about terascale, petascale, and then most recently exascale. It had kind of the journey flavor of taking speeds and feeds faster, energy efficiency higher, and essentially taking supercomputing down the path of the next flag to pull down, which was exascale. As I thought about where we are as an industry, our journey, it really is more about the next speed bump. And that's really the journey we are on. And if we step back from whatever we do on a daily basis, we'll realize that that journey is not only kind of our tryst with destiny, if you call it, as an industry, but it's also accelerating in very exciting ways. And that's what I want to talk about. Our role, Intel's role, and your role in getting us to the destination and then reforming our views of the next destination that lies beyond that. So without further ado, what is that journey? I am not writing, and I'm not talking about, as I said, the next 2 to the power whatever number, double precision flops anymore. I'm talking about mankind's journey through essentially the phases of intellectual insight and conquering new frontiers. Empirical observations was the first paradigm, has been here from the dawn of time, ever since we were able to see and sense. Second was the theory and experimentation phase that has been around for centuries as the analytic sciences grew as a very specific endeavor in humanity's quest for knowledge. The third was really modeling and simulation. And modeling and simulation came about with the dawn of the digital age, as the tools, called computers, became available for us to not only observe the world, but model and predict its behavior. The fourth paradigm, and that's the journey we are on and accelerating towards, is really freeing us as a society from the constraints of the third paradigm that is only being constrained by what we have understood so far, seen so far, and modeled so far. And it's really taking us to a much more expansive frontier where data is telling us things that we couldn't have if we simply tried to put it in the mold of learned knowledge or analytical frameworks that we have honed over centuries. And that is all enabled by the massive proliferation, the ability to capture, to store, and most importantly, compute on that data. Humanity's quest then, enabled by the work you all do, we all do as an industry, is to then free ourselves from essentially the constraints of being intellectually human. So let's talk a little bit about what needs to happen to realize that fourth paradigm. The fundamental aspect of this is around an intelligent hierarchical infrastructure for insight generation. Why is it intelligent? It's intelligent in multiple forms. It's performant intelligent. It's energy intelligent. It's aware and intelligent about where data is, what is the data, and where compute has to lie relative to that data. It's hierarchical. It's hierarchical on so many dimensions. It's hierarchical as to where the action is, from the edge, the massively exploding intelligence sensing of the world, to the data centers that capture all of that and make long-term and short-term decisions. It's multi-location. It happens in the smallest of devices, like a cell phone, to the most massive of supercomputers, like the top 1 machine or the top 10 supercomputers of the world. Yet, it happens with a seamless abstraction across that hierarchy, facilitating an unprecedented level of software efficiency, software productiveness, and it's essentially an explosion of ingenuity in the software space to use this infrastructure. New capabilities, new uses, new frontiers for mankind. It has some massive implications on then things that we have taken for granted and continue to take for granted and evolve through our respective efforts in the field of computer science. The first is around expanding computational models. And we call it the X plus NN plus memory. And if you look at this, you can describe it one of many different ways, but the simplest way is to say X is whatever you think we are doing today. Whether it's solving partial differential equations, whether it's basic or rudimentary table-driven analytics, or even stochastic and probabilistic methods for machine intelligence. Neural network then adds this whole notion of being able to sense with a completely different paradigm. And then memory is what gives it sustained intelligence in remembering that what has been learned and building on top of it, as opposed to having to relearn simply because computation starts from an epoch. The second thing, and this is in many ways probably the most exciting thing, and I say this not because I was an old software guy, because I really do believe this to be true, is the notion of the task of programming changing from an explicit task. You are a programmer, you are doing programming, to this being implicit in the way you get your job done. And we'll talk about this in a second. It's really about problem-aware and hardware or architecture, or the tools for solving that problem, unaware. This is an audacious goal, but if we get there, we would have transformed the way the tool of a computer or a digital computing device is used. So let's talk about that. That thing that I said I'm excited about, not because I'm an old software guy, but because I really do believe that this is the transformational element of how this field of HPC, supercomputing, and AI touches every life on the planet. The first is intent. And intent is really to understand the programmer's goal through natural forms of interaction. Right? We can say a lot about it, but it's very simply not having to have the human being think like a computer, but the computer to think like a human being. The very first time I had to write a massive matrix multiplication, I'm an applied mathematician, not a very good one, obviously, but an applied mathematician that I had to multiply two matrices that didn't fit on a particular node's memory, and I had to learn what MPI was and all of those things. And I forgot essentially what matrix multiplication was after a while because I was so concerned about the computer science part of implementing the computation. So what I could write in a loop suddenly became lines and lines of code executing through layers of the infrastructure hierarchy. The second one is not just making it easier for the intent to be transferred to the computer, but also to have the computer invent and be your co-programmer, if you will. Finding ways to understand the intent, to come up with the tools, scouring code, scouring best-known methods, scouring correlations in existing repositories of code, coming up with new data structures without us humans having to invent those data structures at computer speed. That's really what invention is about. It's no longer the human invention that's driving it, but the human unleashing the computer to do its own invention. The third is adaptation. And this is really around autonomously evolving software to be more effective, to be more performant, and frankly, to be more accurate. And so with these three tenets, we think that programming, it's not programming models, but programming has to be rethought as a task in computer science. And the most important thing is then the systems and the architecture of systems that those things get programmed for has to fundamentally change to support it. I'm going to focus on three specific areas. One is compute, one is memory and storage, and the third is interconnect of large distributed systems. In the area of compute, we have seen tremendous progress over the decades on going from scalar to vector, and now at the dawn of the age of spatial computing. We've gone from mathematical systems being ergodic and well-behaved at high levels of precision, and now exploring either for energy efficiency or performance efficiency goals, numerics at an unlimited granularity, right? And so what we have to do is to look at compute as being unconstrained in how we express parallelism for performance, whether it's structured or unstructured, and unleash the fact that mathematics can only be done at certain precisions on a computer, both correctly and with performance. The memory storage piece is probably one that is exciting in a revolution sense, and that's happening just about as quietly but as profoundly as the compute revolution. In the past, we've asked ourselves the question of what is the memory hierarchy in this machine? The caches, the many levels of caches, where does it end? We've asked about the storage hierarchy, and increasingly over the last few years as data has exploded, talked about warm and cold tiers of storage. But we've always talked about them as two different hierarchies. And what we have to do is converge them into a notion of one single hierarchy. Of course, they're going to differ in performance. They're going to differ in capabilities like persistence or volatile. But they have to function in its intelligent hierarchical system architecture as one continuous hierarchy. Be programmed that way, be managed that way, and be manifested in the performance and the capability of the system that way. The third is around interconnect. Interconnect came about in distributed systems as connecting things that computed. And yes, over time, became more efficient in communication. Interconnects have to evolve to be more speedy, less energy consuming, with great technologies like silicon photonics and other things. But they also have to become part of that intelligent system hierarchy. Within system interconnects have to extend to understand the hierarchy or the semantics of that converged memory storage hierarchy. Between intrasystems in that end-to-end hierarchy have to understand where those boundaries of semantics exist and how they can be abstracted away to provide, again, that one seamless view of a hierarchy with heterogeneous elements or levels of hierarchy. A huge, huge way that the role of the interconnect changes from connecting things and essentially being a network to being a first-class citizen of the computing hierarchy. For us, delivering an unmatched compute platform that then embodies this ability to have unconstrained parallelism, workload-targeted optimizations, be freed from having to put everything in one model of compute, and being able to apply the best architecture in silicon to various workloads becomes the sustaining way to build these computing systems of the future. It's a combination, and it's driven by both technical realities as well as the economics of this business, where you have to have general purpose performance. Something that can run everything, perhaps not as well or as optimally as if you built optimized accelerators. And you have to build them in a platform that can seamlessly support from both a software as well as a hardware infrastructure perspective that capability in an easy-to-use and deployable way. So when we look, for instance, at the XEON family, we think of it as, and see it as a leadership general-purpose platform. It has many of the capabilities that almost everything needs. It evolves. It supports a broad set of programming models and software. But most importantly, going forward, it also supports in a very optimal way the addition of workload-specific accelerators to the platform. No longer is there a debate about, do you remember in the famous, I forget which year it was, we had this offload versus onload debate around TCP/IP. That's a moot point today, because that battle doesn't exist. It's not about what you onboard or offload from a CPU. It's about what works together best where. And with the advent of things like neural network processors, FPGAs, as well as discrete GPUs, the role of the CPU is not to see it as a competitor, but to see it as an enabler in an overall platform that has the capabilities to run general purpose, but also scream at workload-specific optimization. We have in research where life goes beyond this as we try to implement as quickly as possible those principles of uncompromised parallelism and freedom from numeric boundaries. And that's all around the data flow architectures that intense data-driven computing necessitates. It's around neuromorphic computing that has certain tasks that can be accelerated with far lower energy expense and comes closer to representing the programming models of the brain. And then eventually a very active foray into quantum computing that looks at breaking this basic boundary of binary or Boolean logic and achieving, for very specific problems at least, a tremendous breakthrough in the raw digital compute performance. All in all, an unmatched computing platform. It's not about A versus B. It's about A plus B plus C delivering every need that the software community is going to have in terms of performance and efficiency. So if you look at this, you go, my God, this is quite a journey. This is quite a journey. It's probably going to take a long time. Like any journey that's worthwhile, it has its toils and it does take its time. But if you step back for a second, every step, and I chose this picture specifically, not because I'm a mountaineer, because I understand, at least I appreciate how hard it is to look up once in a while at a peak that's still some ways off and take the next step and be excited about it. Our industry is evolving, taking that step every day. We at Intel are taking that step every day and getting closer and closer to that peak. I want to talk about that next step today. We recently announced on 8/8, which is not as cool as 11/11, I know, the Cascade Lake Intel Xeon Scalable processor. It's shipping for revenue in 2018, so it's not near the peak. It's here at your feet today. It's got leadership performance. It has a set of microarchitecture enhancements and higher frequencies that provide a tremendous boost in performance for things like HPC and AI. And most importantly, again, in that platform view, it has some tremendously revolutionary breakthroughs in terms of supporting new models of memory and storage hierarchy convergence. And that's really through our Intel Optane DC persistent memory support, a unique capability in the industry. So let's talk about that a little bit. As I said, converging the memory and storage hierarchy may not seem quite as prolific in the press or in the community as coming up with new algorithms for convergence or microarchitectural enhancements. Yet it has a profound effect on the performance of systems and the efficiency of and effectiveness of being able to use them. In the past, we've had two hierarchies, memory and storage. And then there was an abrupt barrier between the two. You actually had to understand when you were accessing a storage device, the semantics were different, the performance was different, you programmed differently, the infrastructure software or operating systems saw memory devices and storage devices differently. As a result, you had to, as a programmer, decide how you were going to place data on each side of the boundary. And if you got it right, it paid off. If you got it wrong, you paid for it. Most importantly, it left value on the table because we didn't have the option till now of actually using storage class capacities, storage capabilities like persistence in a memory-like access, close to memory-like performance, right? And that is really what the Intel Optane DC persistent memory does. It provides you better performance because you don't go out over storage semantics to storage devices. It provides you higher memory capacity. Don't think of it as higher storage capacity. It provides to the node, using the memory semantics it supports, higher memory capacity. And perhaps most excitingly, enables new usage models. New usage models, one of them that I've always been very excited about, and I hope to see it soon unleashed in the HPC community, is a supercomputer that uses this persistent memory in every node and essentially boots in seconds. Wouldn't that be revolutionary? So obviously for us, this is very exciting. For the industry, it's very exciting. We've actually shipped this technology in product to Google already for revenue. And we see a tremendous opportunity, a tremendous demand in the marketplace as we ramp this technology fast in 2019 with the Cascade Lake processor. But we didn't stop just at Cascade Lake. The next step as the relentless train of innovation on Xeon continues. We also announced very recently the Cascade Lake Advanced Performance Processor in the same family that extends Cascade Lake to an entirely new level of performance, especially for technical computing, high-performance computing, and AI. It's 48 cores and 12 memory channels. The 48 cores with a per-core architecture that's tuned for very, very efficient and high utilization of typical applications we see is architected for a very demanding range of workloads, and the total compute capability, peak and efficiency provides a tremendous opportunity to take the applications of today and move them to new levels of performance. Along with the 12 channels of memory, there is more memory bandwidth than any CPU today. And I would even say in the near foreseeable future. The combination of those two, giving it the flops and giving it the bytes per flop that these applications crave in a general purpose computing infrastructure is a breakthrough. It's ramping in first half of 19, and I know we're excited to see many of our partners and friends in the HPC community clamoring for this date to be sooner rather than later. Let's talk a little bit about that leading performance. It's easy to say on a foil it's got leading performance, right? We talked about benchmarks before, and I think to this community I don't have to talk about LinPack and Stream Triads. I thought Jack was here somewhere. Was it him? No, there you are. But obviously, numbers that we measured in two-socket configurations against the shipping current generation competition are pretty telling. These numbers are measured not on a simulator, not on a performance estimator, but on pre-production silicon. LinPack, up to 3.4 times. 1.3 on Stream Triad. Again, a testament to that memory bandwidth capability that is not just in the 12 memory channels, but the microarchitecture that supports a very high utilization of that memory bandwidth. That's for traditional HPC. We also looked at deep learning, which is increasingly becoming a very important part of the computing portfolio of usage. Up to 17x images per second on something called a ResNet 50 kind of image recognition application using that topology. In itself, it's interesting. It's both a benchmark and an application. And literally, we looked at how much progress, that 17x is not against anything else, but our best performance on Xeon, and how much progress we made in one single generation in improving with some of those features like VNNI, the deep Intel deep learning boost that I talked about for Cascade Lake AP that this provides. But really, at the end of the day, you say, yeah, Raj, but that's benchmarks. We all know what benchmarks can do. They're a little bit like Las Vegas, right? I mean, you can be whatever you want it to be. And you can show it in any different way. What it really comes down to is the applications, and not just applications, but applications our community uses every day in its most prolific forms. If you look at MILK, which is a quantum chromodynamics code, or you look at WRF, OpenFOAM, NAMD, and YASC, right? I don't have to explain what these are. You probably use them every day. You probably are working on them every day. You probably are cursing them sometimes for some of their complexities and brittleness every day as well. But whatever you're doing, you're using these as a very representative set of what the community uses to get their job done today and will for a while. Again, numbers like 1.5 to 3.1 on the stencil codes. And so if you're looking at stencil codes, this is an unprecedented level of performance improvement in a single generation. So real-world applications, these are all measured on pre-production hardware. So these are not performance simulated on a single node. And we see this as a tremendous way to continue to drive that performance capability and that hardware-software spiral towards that peak. In terms of availability of systems, we have almost all the leading HPC system vendors working with us actively to have systems ready with Cascade Lake, and therefore give you the ability not just to see what this processor could do, but to put them in action in your organizations. Very, very excited to have this body of partners so actively engaged and seeing the same opportunity that we do, and partnering with us to make that happen for you, the end users. Did I go back? But nothing is more special than the first, right? And I'd like to talk about HLRN. I don't know if anyone from HLRN is here today, but Dr. Reinfeld provided this quote for us. A very large supercomputing center, well used for science and industry in Germany. They have, using an Atos-based system, been looking at Cascade Lake advanced performance, decided to deploy it at scale, and are really looking forward to some stunning improvements for their customers in the performance of applications and the capability that the supercomputer will provide for the next generation of their deployment. Again, we see many, many more after this, but the first story is always very special. And so with that, I'd like to thank HLRN. I'd like to thank Atos for their partnership in bringing this system to reality as the #1 Cascade Lake advanced performance system. I am hitting the wrong button today. The next first I'd like to talk about is the first Optane DC, data center persistent memory, in a supercomputer. And this is for Dan and folks at the University of Texas Advanced Computing Center. And I think Dan talked about this earlier today, if I'm not mistaken, the Frontera system, making a bold step forward in providing Optane DC memory, persistent memory, for actually changing not only the performance characteristics of the machine, but giving the software community a tool to start experimenting with the capabilities that could bring about completely new different system features. For instance, re-architecting the file system with this as a layer, a hot layer, if you will, changing the way checkpointing is done, and therefore affecting system efficiency through much more distributed and efficient checkpointing mechanisms. Looking at this as memory capacity instead of large, what we call fat nodes, for in-memory databases and other out-of-core computing algorithms, and providing a new level of memory hierarchy to support those memory, both capacity as well as bandwidth-sensitive applications. Again, a tremendous asset for the community to have in a supercomputer, and we see this as one of many, many soon to come, and start that spiral of what this new capability can generate 5 years from now. So thank you, TAG. So in summary, I'd like to leave you with 3 thoughts. It's a new paradigm of high-performance computing. It's here. It's around enabling unconstrained parallelism and numerics for algorithms of today and the ones to come. It's about converging the memory storage hierarchy, and it's about using the interconnect not as a network, but as a fundamental first-class citizen of the computing hierarchy. And it's a new paradigm of high-performance computing that we are heading to, where it's a whole different set of developers and a whole different set of applications that we can even think of today that get run on those machines. We are investing in and have an unparalleled set of assets to lead this transformation. Because this transformation has to happen not in a single portion of that hierarchy, not in a single pillar of that hierarchy, not in a single piece of silicon, but across all elements of the platform, the system, and software. But most importantly, what I am most proud of is our partnership with a much broader ecosystem outside that enables us to become co-travelers and vote for success together. And finally, I'm very excited by the next step in this transformation. Sure, it's not the end destination yet, but it takes us further down this path of realizing platform capabilities we didn't have, of realizing performance we haven't been able to deliver, and most importantly, stoking the imagination for the future, for those next steps that need to take us to the peak to happen accelerated. With that, thank you very much. Have a great Supercomputing 2018. Onwards and upwards.